And welcome to today's Hi5 seminar. We have a speaker from Mississippi State University today, Mr. Nate Phillips. He is a PhD student in the Spatial Perception and Augmented Reality Lab, working under J. Edward Swan. And he's going to be talking to us today about some of the research that he's been working on in augmented reality and X-ray vision, I believe. So without any further ado, Nate, I'm going to turn this over to you.
Awesome. Thanks. So, as Dr. Adam Jones just mentioned, I'm Nate Phillips, and today I'll be talking about augmented reality X-ray vision for accurate perceptual situation awareness at action space distances. Now, that's a real mouthful of a title, and we'll get into some of the details on that later and throughout this slideshow. But for now, I'm going to tell you a little bit about myself and my lab. So, as previously mentioned, I'm from the Spatial Perception and Augmented Reality Lab, the SPAR Lab, at Mississippi State University under Dr. J. Edward Swan II. Our projects focus on perception and situational awareness, but we also do a little bit with display calibration and display technologies. As you can see here, we get to play with a lot of really cool AR apparatuses and devices. So, it's a really excellent place to work. I highly recommend it. So without further ado, let's get started on our primary topic, X-ray vision. Roughly speaking, X-ray vision is the ability to see through opaque barriers and understand what is behind them. This term isn't scientific in nature. It was originally developed by comic book writers to describe a superheroic power. Most famously, it's ascribed to Superman, but I believe the term actually predates Superman comics. Of course, in reality and in this application, X-ray vision doesn't actually involve X-rays at all. It was simply a good way to describe the effect to viewers. So what are the potential use cases of X-ray vision? There are a fair number, and I'm only going to cover a few here, but they include surgery and medical applications, navigation and exploration applications, and then disaster recovery and SWAT team reconnaissance. So as an example, why you might need X-ray vision for surgery. Say you're a medical doctor who's performing a brain surgery, for example, and you want to find a particular clot or tumor, and you have to position an instrument very precisely to do so. I believe current standard practice is to look at a 2D image on a monitor, then adjust the position of your scalpel and back and forth until you have an accurate placement. It would be very much easier if a doctor could view this information egocentrically and adjust the scalpel without having to look up from their work. For navigation purposes, the ability to see around corners or see through walls or even see inside crates or boxes could potentially be useful, especially in industrial applications. For these last two features, these are roughly the same task, though from a different angle. In disaster recovery, you want to investigate a building, say, that's been hit by an earthquake or maybe a damaged nuclear reactor. These are places that humans can't readily go because it's very dangerous, but you still might want to find information. Are there any victims nearby? Is there anything of interest in a room? And so you might need to find data on that room and on that area and send it to a human remotely. In SWAT team reconnaissance, the issue is broadly similar. Instead of danger from natural disasters, you're facing danger from potential human interactions, though. And as such, you want to know the details of what's going on in a room before actually sending people in. And of course, there are many other use cases, but these are the ones that we'll primarily focus on. So here are a few X-ray vision prototypes and methods from previous research. As you can see, all of these are navigational or explorational examples. You're seeing the wall and seeing beyond it to something that's going on the other side. You can see that each of these methods has different visualization approaches, different ways of making the saliency of what's beyond the wall more apparent. And here you see another navigation prototype on the right, and on the left you see a surgical or medical application. In the surgical or medical application, you see the organ sort of overlaid onto a surgical dummy. so that perhaps a surgeon or a student could more precisely position a tool or know where those organs are. However, all this research is really quite interesting, but there are some significant gaps. So far, there has been a lack of depth perception measurements. There's been a lack of comparisons between real-world perception, what we perceive as distance to real-world objects, with comparison of what we perceive virtually to X-ray vision targets. And this is important, A, because depth perception in many of these use cases is really very significant, and B, because in virtual and augmented reality, depth perception isn't necessarily as accurate as in the real world. So for example, in virtual reality, distance has often been underestimated in what's called the foreshortening effect to distances in the real world. In augmented reality, the situation is a little more complicated. Some studies have found overestimation, some underestimation, even a few some accurate estimation. This seems to be related to the sort of AR intervention, the real world environment, and so it's a little more complicated. But this just goes to underscore the interest in and the research potential for investigating X-ray vision in augmented reality. Secondly, X-ray vision has an unclear impact on situation awareness. Now, we'll go more into situation awareness a little bit later in this presentation, but roughly speaking, situation awareness is a user's grasp of and understanding of a task or variables related to that task. If we're thinking of a navigational example, say someone is trying to find their way to a particular pub, and they're wearing an X-ray vision system. If the X-ray vision system helps them to get to that pub more quickly, more efficiently, more safely, then that's a positive effect on situation awareness. If something about that X-ray vision system, X-ray intervention, has a negative effect, maybe there's too much distracting information, maybe the user gets confused, then it will have a negative impact on situation awareness. Broadly speaking, we hope that that X-ray vision has a positive impact, but tests and research have not really been done in this direction. And finally, we're excited about researching X-ray vision because there are some newer technologies that could potentially increase the effectiveness. The last couple of generations of AR headsets, for example, have been really quite impressive, both in terms of new technology, better field of view, better frame rate, and in terms of incorporating older technologies more fluently and more easily than previous solutions. So this brings us to our task, SWAT team room entry. SWAT teams are often called upon to investigate room to room in some high-risk situations. For example, maybe a hostage situation, maybe some other high-risk room search, maybe a drug bust or something. During these interventions, SWAT team members have to go room to room and investigate each room. This has high uncertainty and high risk. It's very dangerous, and the SWAT team members are prepared to use physical violence. As a result, there's a significant potential for negative outcomes. To see this, just look at the incidence of swatting in the US. Swatting is where SWAT team members are called upon a completely innocent person. Unfortunately and sadly, many of these incidences have resulted in that person's death. And so this innocent prank has, because of poor situation awareness, resulted in someone's death. We posit, though, for this task of room entry, that we could reduce these negative violent outcomes and deaths by giving SWAT team members information about the contents of the room before they enter. Doing so will decrease the uncertainty. It will allow the SWAT team members to observe the context of the room and the environmental information in the room, and so better select between violent responses and perhaps better non-violent responses even before entering. As such, this should drive down negative violent outcomes to these situations, and we are hopeful for that result. That is sort of the goal of this research. So, to further define the task, we have a SWAT team that's going to go investigate room to room. But what other parameters do we have? Well, we're focused for this research on the medium field, or Cutting's action space distances. These are distances anywhere from 1.5 to about 30 meters. Distances where you can see an object and act upon it, but you can't immediately reach it. You have to walk over and do something to it. Excuse me. And even within this distance, we're really focused on distances out to about 15 meters. Secondly, we have to have stereo room information for X-ray vision to work. In order to get this, since most rooms don't have stereo depth cameras already installed, we'll have to incorporate a robot into SWAT team protocol. This is a pretty significant change of pace. SWAT team members are usually very efficient and quick in their actions, and a robot inevitably slows them down. So we look a little bit at previous research. How can we incorporate some of these elements into SWAT team practice? This brings us to the X-ray vision system. This is our solution for providing X-ray vision to SWAT team members. We make use of, in particular, the Magic Leap AR headset. It has two very important features that allow us to do this. One of these is fiducial tracking, and the other is accurate SLAM tracking. SLAM tracking, or simultaneous localization and mapping tracking, is how the Magic Leap keeps track of its position while also building a map of all the features and geometry around it. This enables it to know its position, its orientation, all of that with respect to the room it's in. Fiducial tracking, on the other hand, allows it to center this coordinate system on a particular fiducial or 2D image so that its mapping can be localized. And of course, as previously mentioned, we also use a robot vehicle and a stereo depth camera to get the room image as well. Here you see the sort of flow chart of this X-ray vision system. The stereo depth camera takes the 3D room image and it is mounted to the robot, which sends this image to the Magic Leap headset such that it can be displayed to the user. The Magic Leap and the robot have to synchronize their positions, and they do that using a universal tracking fiducial, allowing each of them to know where the other is. So this is a fairly complicated system. There are a lot of moving parts, a lot of details. It's reasonable to ask, why not some simpler approach? Why not, for example, a SWAT team member using a tactical mirror? This is about as simple as it can get. There's no electronic parts. You just have an officer and a mirror. Or alternately, why go through all the rigmarole of an AR headset? Why not just use a robotic entry vehicle and have a 2D through the camera view to inform the SWAT team members of what's on the other side? Well, the answer is there actually are some significant advantages to an AR approach. First, in AR, the data is presented egocentrically, which means from your own point of view. In previous research, we have found that egocentrically presented data is much more accurate than exocentrically presented data. An egocentric judgment, for example, would be if I asked you to look at an object in your room and to judge the distance to that object. You could usually do this very accurately. An exocentric judgment would be if I asked you to see two objects within your room and then visualize and estimate the distance between those objects. These depth judgments are very much less accurate than egocentric depth judgments, and as a result, the AR headset has an important advantage in this regard. However, also, and in particular I'm going to focus on the mirror approach here. The mirror approach is very quick and easy to use. However, there are important offsetting and inversion effects that have to be dealt with. The SWAT team member can observe the data, but before it's useful to them to get it within their own point of view, their own frame of reference, they have to invert it and offset it. And this is cognitively challenging, especially if at the same time you're trying to predict what's going on and to understand and formulate a strategy. This will slow down reactions and results and may introduce negative effects to situation awareness. Now, secondly, I'll also focus a little bit on the 2D robot image. This suffers from what is called in the research a keyhole effect, where actions and distances are misjudged and misestimated when viewed through a singular 2D image. Part of this seems to be that the 2D image has a very narrow field of view, especially as compared to our full vision. And as such, this has cognitive effects that throw off our distance perception. So both of these approaches, while potentially useful and certainly simpler than the X-ray vision system, have their own negative effects that might impair judgment or reduce situation awareness. This brings us to the ways in which the X-ray vision system does promote accurate situational awareness. So to talk about this, we have to take a bit of a step back and talk about human depth perception. Human depth perception is based on a variety of visual elements called cues. These include things like occlusion, stereopsis, convergence, accommodation, brightness, contrast, and various other things of that nature. For this use case, we'll primarily talk about the cues that are most important to the X-ray vision system, but know that there are a wide variety of cues out there as well. So briefly, one of the primary cues in AR research that has been heavily investigated is stereopsis. Roughly speaking, this is the ability for our two eyes, which each are capturing a single 2D image, to combine that 2D image into a 3D depth-based image. This cue is very important in the near field, up to about 1.5 meters, but its effectiveness starts falling off past that. Since we're working in the medium field out to about 15 meters, it's still an important depth cue, but it doesn't have the strong predominance as it would within arm's reach. Thankfully, to offset that cue, we have another cue called motion parallax. With motion parallax, you would see an object, and if you offset your head, you would see how that object moves in your field of view. Based on those differing perspectives, you would have a depth understanding that could be generated from moving around that object. Now, when I talk about motion parallax, unfortunately, without video and without an egocentric display to see it through, it doesn't really quite have the same effect. But suffice to say that motion parallax helps you feel like an object is really there in a way that many other effects don't necessarily have. Now, these are two cues that help support depth perception in X-ray vision. Occlusion, on the other hand, is actually a negative effect that must be overcome in a way. So occlusion is, for us, if there's one thing in front of another thing, like if I were to hold up my two hands here and you were to see the hand in front or the hand behind, the closer hand would block the view of the farther hand, preventing you from seeing it. This is sort of how we understand opaque objects. Unfortunately, for X-ray vision, you can see this in the image on the right. For X-ray vision, we are trying to visualize something inside another opaque object. This is problematic because our visual system doesn't want to accept that. It sees an opaque object, an object in front, and says, okay, this has to be in front of this other clearly opaque object behind. And so, as again on the right, oftentimes X-ray vision will push the virtual image a little closer to the user because of this effect. Now, to counteract this effect, we have considered what we call the window metaphor and what some other researchers have termed cutaways. Essentially, we have a bounded rectangle through which you can see the virtual image or visualization. That corresponds with motion parallax. So if you shift your head from side to side, you'll see a different view of the virtual image. And the reason we think this will be more effective than just a singular unbounded virtual image is that we really quite well understand windows. If you were to walk up to a window and look outside it, you understand that what you're looking at is beyond the window. And so using this metaphor, I think, may aid human depth perception. The proof is in the pudding, of course. We'll see how the results turn out, but we think this is a really excellent approach to increasing accuracy in X-ray vision. And finally, I want to briefly also mention field of view, since it's likely proven to be important in particularly virtual reality. Higher fields of view seem to be correlated with better distance judgments, particularly in some of the newer virtual reality headsets. Here, though, we expect that this probably will not be a very significant feature, especially as we bounded the field of view here artificially with the window. This brings us to situation awareness. Loosely speaking, situation awareness is an operator's grasp of the critical information for a given problem or task. Here we're going to go quickly back to the metaphor we established earlier. The idea of someone trying to find a particular pub while wearing an X-ray vision system that lets them maybe see through walls. With that X-ray vision system, it will show them perhaps some additional new information. If that new information is helpful and helps them find the pub without experiencing negative effects for the information they can already see, then that will be a positive impact. Otherwise, if there's some feature of the system that causes problems, for example, if there's so much information and that information is so distracting that they lose track of real-world variables like, the position of cars on the street, their position on the sidewalk versus on the street, things like that, this would have a negative impact on situation awareness. And you can see if you earn extra navigational information but lose track of whether a car is coming your way, that's a pretty significant difference. So to frame situation awareness here, we have a sort of feedback loop here that kind of plays through this. Everything we do occurs in a feedback loop. We understand our environment, we attempt to act upon it or not, and then we modify our understanding based on what happens. Situated right in the middle of this is situation awareness, and it has 3 levels: perception, comprehension, and projection. Each level is built on the previous foundation. Without perception, there can be no comprehension or projection, and without perception, you can't really understand the environment at all. So in our example of the navigationally challenged friend, the variables that might be of interest are, say, the location of the pub, the perception of cars on the street. All of these involve perception and are the first step to comprehension and projection. Understanding that there is a car on the street, for example, you might wonder which way is it going. If the car is facing you, you might comprehend that it's going towards you. If it's facing away, you might comprehend that it's going away from you. And then from that, you can understand projection. If it's coming towards you, maybe you should move. If it's going away, maybe it's of no concern. This is a very high-level view of situation awareness, and there's been a lot of research in situation awareness I really encourage y'all to check out. In particular, it focuses on air traffic control and air traffic control visualizations, and it's really fascinating stuff. For the purposes of this experiment, though, we are aiming to measure how the X-ray vision system affects perception, both because it's the first level and because it is sort of the most important level. Without accurate perception, how can you do comprehension or projection? And this brings us to our next question. In order to measure perception in an X-ray vision system, what do we need to do? Obviously, since this is occurring through a wall, you're seeing through a wall some virtual target beyond. Most of the direct measurements we often use, direct blind walking, beanbag toss, even triangulated walking, don't really work here because there's a wall in the way. There is one direct measurement that we could use, but it tends to be rather variable, so we opted not to use it. It is verbal report, and as mentioned, it tends to be rather variable. What we did decide to use, though, is something called triangulation by pointing. You can see an example of triangulation by pointing on the right. In triangulation by pointing, a user will observe a target, and once they have fixed that target's location in mind, they will point to that target, close their eyes, and walk for a certain distance without vision, continually pointing at the target. Once they've walked the correct distance, they're stopped, and the angle is measured. As you can see here, the intersection of the 2 lines is where the perceived target is, where it persists. That is their depth of judgment. This hasn't been used extensively, but as you can see here on the left, it has accurate results up to about 15 meters in the real world, to clarify. when you close your eyes and walk for a certain distance and point. 15-meter distant targets tend to be accurately represented. And as you can see, and as research we would expect, if your eyes are completely open, you have accurate distance judgment up to maybe about 25 or more meters. And so this is the approach we decided to use to measure distance perception through a wall. And using some pilot data, this is what we have. This is, of course, not necessarily rigorously collected data. This is a small number of participants, mostly lab partners, but this sort of gives you a feel of how the data may look in the future. With eyes open, as before, distances are highly accurate. With eyes closed, distances seem to be accurate up to about 15 meters, but after that, distance estimation seems to fall off and be foreshortened pretty significantly. This brings us to the question, so if this is distance perception in the real world, what will happen when we try this out on the X-ray vision system, our X-ray simulation? And the answer is we haven't gotten to this yet, but we shall see. We think there are a large number of variables and reasons why this is quite encouraging and why this may give us really strong results. The window metaphor, improved display technology, triangulation by pointing, but we don't really know yet, and that will be in the research, but we're quite excited to find out. So, I hope this presentation has sort of explained and helped you to understand what is meant by the title, Augmented Reality X-ray Vision for Accurate Perceptual Situation Awareness at Action Space Distances. It's a really exciting topic and really interesting, and I encourage you all to look into it. And here, to end out this presentation, I have a few prototype shots of the X-ray vision system in action. This isn't necessarily indicative of what the final result will be, but this sort of gives you an example of how the X-ray vision system would work. So here you have a chair that's being visualized, and on the left side you can see through the door of the chair, and on the right side you can see it directly overlaid onto the chair. Now, as mentioned previously, there are a lot of things in this, particularly motion parallax, that don't really make sense without being able to see it through an augmented reality headset. With the augmented reality headset on, you get the feeling that the chair is really there. And of course, this is also a fairly early prototype visualization. For example, it doesn't have any color and the point cloud is fairly large. So here is another example from a slightly more advanced simulation. Here you can see the point cloud has color and is much more fine. Again, though, without the motion parallax and stereopsis from viewing it within an augmented reality headset, it misses the mark by a little bit, but hopefully this helps you understand what the X-ray vision system is intended to do. So thank you so much for listening, and thanks in particular to Dr. Adam Jones for hosting us and to the Hi5 labs as well. Thanks to the NSF and Mississippi State University for funding my research and work as well. Are there any questions?
Hi, Nate. Thank you for the excellent talk. I'm going to, if you could unshare your slides, I'll get us both on the screen. There we go. Awesome. Cool. So, good news, bad news situation. The good news is we have recorded your talk. The bad news is, as the people watching on YouTube in the future will see, is the stream to YouTube, well, let's just say it disappointed me greatly. No, it stopped streaming. The Zoom connection still worked fine, so we're able to record the whole thing. But for some reason, the stream to YouTube did give way on us. But, like I said, we got it recorded, and we'll get the whole thing up on the website as soon as we can. So there won't be any questions from the audience. However, there are a few things I'm curious about. So you're using the Magic Leap? Is that what I
Yes.
Yeah, because that was roundabout where the stream started giving trouble. So I stopped listening for a second to try to troubleshoot, and just kind of got a little bit from what I saw there. So why did you pick that particular piece of technology? You probably did say it, but
Well, in particular, since the HoloLens came out, the generation of AR displays that we've found all have been really quite promising and quite strong. When the Magic Leap came out, we found a really excellent set of guides to set up things like fiducial tracking and slam tracking,
Mm.
and B, a really excellent system as well. I'm not as aware of the full array of AR headsets as I could be, but the HoloLens and the Magic Leap are together the two most promising AR displays I've worked with.
Mm. So, a mutual colleague of ours, Gurjat Singh, uh, looked at the effect of accommodation on depth perception augmented reality.
Mm-hmm.
So, I believe the Magic Leap has dynamic-ish focus. Like I think it has like 2 or 3 focal planes
I
with
think so,
incorporated
but
eye
I'm not
tracking.
sure.
Are you looking at anything with regard to that?
Currently, no. Currently, our focus is on stereopsis and I lost the term, motion
Hmm.
parallax. Sorry, um, but I think that would be an interesting thing to look at in the future, though,
Cool, cool.
especially
So,
as the Magic Leap apparently supports it quite well.
yeah. Well, assuming that it gets the eye tracking right, because
Mhm.
it's assuming where you're accommodating your lens is focusing based off of your convergence, I believe.
Mhm.
So at the end, you were showing your point cloud. How did you well? Did you use the depth sensors on the headset to generate those, or did you record those with
I
something
think you're
else?
cutting out here. I can't hear your voice.
Okay, can you hear me now?
Still can't.
Still can't. Hmm,
It's kind of odd.
that is kind of odd.
Did your mic become unplugged?
Nope. Yeah, it's I'm still getting audio in the equalizer on this end. Now you're gone. Okay, folks, we're living in the age of Zoom and Skype and
Oh, hey, I've
Teams
got
and whatever. So these things happen.
yeah.
Yeah, I've got I just now got an unstable connection warning in Zoom. So what you probably didn't hear me say was looking at the audience dramatically and saying we're living in the age of Skype and Zoom and Teams and all these things, and you know this is everyday life now. Uh, so anyway, my question was about generating your point cloud. Did you use the depth sensors in the headset, or did you use something else to get your point clouds?
So to generate the point cloud, we use a stereo depth camera, in this case an Intel RealSense, and I forget the exact number,
Gotcha,
but it generates the point cloud and it generates all the depth that's associated with that.
gotcha.
And it's actually really excellent. If you start it and then move it around, it keeps the point cloud centered or offset correctly based on where
Good,
the recording started.
good, because that's challenging.
Oh, yes.
Um, yeah, I actually really love depth cameras. They're just fascinating pieces of technology, especially the different ways that they're implemented. Really neat. So
I also highly recommend the Intel RealSense.
yeah,
Very, very strong hardware.
awesome. I'll have to check that one out. Okay, so since there are no questions from the audience right now, since we don't have one, we're going to go ahead and wrap it up there. And Nate, thank you for coming and speaking with us today. You're our last speaker of the summer. We're looking into continuing the seminar series into next semester, but we're going to take at least a few weeks off, in the meantime, because, classes are starting back and, life gets busy. But again, thank you for coming and speaking with us today.
Thank
And
you for hosting us.
oh, happy to have you here, dude. And for those of you who will be watching in the future, if you're interested in this kind of material, please like and subscribe to our channel because we're going to be posting more stuff like this in the future. Yeah, the summer series went really well, and I got some requests from folks saying, "Hey, can you keep it up?" And yeah, I think we can do it. It's fun for me, and hopefully fun for you guys too. So with that said, everyone stay happy, healthy, and safe, and we're going to sign off. Take care.
Take